So what simple definition we can use here for rearrangement reactions? So rearrangement reactions involve the change in the connectivity, right? Involves the change in connectivity. Change in connectivity. Change in connectivity of what? Of atoms within molecule. Within molecule. Right? Now, what other conditions? Change in connectivity of atoms within molecule with or without use of any catalyst or any reagent, with or without loss of any small molecule from the substrate. Means if there is a loss of some smaller molecule from the substrate, then also you can consider that reaction in a rearrangement reaction. So involve a change in connectivity of atoms within molecule. First criteria, with or without use of catalyst or reagent, right? Means not necessary that every time in rearrangement reaction you involve any reagent or any catalyst. Simple heating also can cause the rearrangement, right? Second, with or without loss of molecules, small molecules from the substrate. So this is the simple definition of rearrangement reactions, right? So, and another feature of this rearrangement reaction is that in most of the rearrangement, 1-2 migration or adjacent migration takes place, right? In some cases, some longer distance also migration may take place, but in majority of cases, in most of the cases, you will get 1-2 migration, right? So most of the migrations are from an atom to an adjacent one, right? And this is called 1-2 shift. Right? And but in some cases we may get this migration may takes place to the longer distance, no problem, but majority of cases this this is takes place. And one more very important feature of this rearrangement is that migrating group never leaves the molecule. क्या मतलब हुआ इसका? इसका मतलब यह है कि जो भी माइग्रेशन होगा इसमें, कोई भी ग्रुप जो माइग्रेट कर रहा है, कोई भी एटम जो माइग्रेट कर रहा है, ये माइग्रेशन स्ट्रिक्टली इंट्रामोलिकुलर होगा। ऐसा नहीं कि बॉन्ड पहले ब्रेक हो गया, फिर वो टहल घूम रहा है अपना सोल्यूशन में, मिक्सचर में, और इसके बाद फिर जाकर के वो जहां पे उसको जुड़ना है वो जाकर के जुड़ रहा है। नेवर। सो दिस इज वेरी इंपॉर्टेंट फीचर. दिस इज intramolecular. Means almost every rearrangement reaction, whatsoever we are going to study here, like pinacolone, Halfman bromamide, any rearrangement, you can take Wagner Meerwein. In every rearrangement, all they are intramolecular, strictly intramolecular. Intramolecular, right? So if you want to, try to understand the, importance of this, I am taking one example. All of you are knowing this Halfman bromamide reaction, Halfman bromamide rearrangement.
Yes, sir.
Okay, something like this RCO
Yes,
NH2 type compound amides, they rearrange to what? R NH2, something like this, right? So this is a kind of rearrangement reaction. So I'm trying to explain this intramolecular feature, or we can say this importance of this intramolecular by taking this example. Suppose that if we have taken this nitrogen 14 isotopic labeling we did here, and here we have taken PHCO NH2, and this is nitrogen 50, right? Suppose that this is given, and both we have taken in a same beaker, same reaction mixture, we have taken these two together. Okay, desired reagent whatsoever required, you can take Br2 and KOH, and it is given what are the possible products in this reaction. What are the possible products in this reaction? So first product, suppose that they have given R NH2 nitrogen 15, second R NH2 14, third PH NH2 14, and fourth PH NH2 40. So what should be the correct option here? What should be the correct option?
second.
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 Second. Okay, now I will change this 15. So now the correct option?
Second and fourth.
Second and fourth.
Second and
Second and fourth.
Second, fourth.
you can see, if you do not know that the nature of this is intramolecular, right? So you cannot answer correctly this question. So these two options are correct. There is no mixing of this group, this migrating group, with this, right? There is no mixing of this phenyl group with this nitrogen, or there is no mixing of this R with this nitrogen. So this is the feature of this all rearrangement reactions, that the migration is strictly intramolecular. Clear to everyone?
Yes, sir.
Okay.
Yes,
Yes,
sir.
sir.
So this is this. Whatsoever rearrangement you have, pinacol, pinacolone, or Wagner Meerwein, or Baeyer-Wilger oxidation, hydroperoxide rearrangement, dinone phenol, every rearrangement reaction, they strictly follow this feature, that it is intramolecular. And this migration, another feature, important feature, that this migration is what? Stereospecific. Migration is stereospecific. This is also a very important feature. Migration of group is stereospecific. Stereospecific. इसका क्या मतलब है बच्चों? मान लेते हैं कि कोई भी माइग्रेटिंग ग्रुप है, माइग्रेट करने वाला जो ग्रुप है, उसकी कोई स्टीरियो केमिस्ट्री है, मान लेते हैं आर है या एस है, मान लेते हैं वो स्टीरियोजेनिक सेंटर है उसके पास, तो माइग्रेशन से पहले जो इसकी स्टीरियो केमिस्ट्री होगी, वही माइग्रेशन के बाद जो है क्या रहेगी? स्टीरियो केमिस्ट्री रहेगी, उसमें कोई चेंज नहीं आएगा। ठीक है, तो माइग्रेशन इज स्टीरियो स्पेसिफिक। तो ये 3 इंपॉर्टेंट फीचर्स हम लोग जो है रीअरेंजमेंट रिएक्शंस में देखेंगे। और देखते हैं बच्चों अलग अलग अनदर फीचर, माइग्रेशन में एक जनरल रिप्रेजेंटेशन हम लोग दिखा सकते हैं। मान लेते हैं कि ए बी इस तरीके से कनेक्टेड है, तो इसको रिप्रेजेंट करने के लिए हम लोग नंबरिंग कर लें। अब ये माइग्रेटिंग ग्रुप W ट्रांजिशन स्टेट के थ्रू कहां से कहां माइग्रेट करेगा, 1-2 माइग्रेशन। मेजॉरिटी ऑफ केसेस में हम लोग को कौन सा माइग्रेशन मिलेगा, 1-2 माइग्रेशन। ठीक है, तो this is an example of 1-2 migration, right? Now the most important point is that this 1-2 shift will takes place in the form of electrophile or in the form of nucleophile or in the form of free radical. Means what I'm trying to say that this rearrangement reaction is observed in carbocations or electron deficient system, or with the carbon ion, it means electron rich system, or with the free radical. So if we compare the transition state in each case, right, when 1-2 migration takes place in the form of nucleophile, when 1-2 migration of any group takes place in the form of nucleophile, then the transition state have the lowest energy. Then the transition state has the lowest energy. How the transition state we can represent for this? The transition state of this migration we can represent like this: A, B, and this will W will migrate like this. This is the transition state, right? So this transition state, when this migrating group migration of any group, here the migrating group is W. So if this W migrates with the nucleophile in the form of nucleophile, then the energy of the transition state is minimum, right? And when this W migrates or migrating group migrates in the form of free radical, then that have a slightly higher energy of the transition state. And if it migrate in the form of electrophile, then the transition state is most energetic. So this is the reason why rearrangement reactions are very common in carbocations, or in case of electron deficient system, it could be nitrogen, it could be oxygen, right? And less frequent in free radicals and very less in carbon ions, right? So when 1-2 migration of any group takes place in the form of nucleophile, the transition state has lowest energy, right? And when 1-2 migration of group takes place in the form of free radical, then transition state have higher energy than this. And if 1-2 migration of group takes place in the form of electrophile, then the energy of transition state is highest. We can see this with the molecular orbital diagram. So see, these are the molecular orbitals formed. When this W migrates in the form of nucleophile, means this W is taking away these 2 electrons with itself in its orbital. So only 2 electrons, this bond, AB bond, this have this electron. So only 2 electrons are there. So we have the electronic configuration of transition state like this. When this W migrates in the form of free radical, then this W will take 1 electron and 1 electron leave here. So total transition state, this have 3 electrons. So now we have this electronic configuration. And once this W moves in the form of electrophile, means without any electron, if this W is moving, so how many electrons we have? So this is the migration of migrating group W in the form of nucleophile. When W in the form of nucleophile means W negative, when the W moves in the form of free radical, and when W moves in the form of cation, right? So this is the energy of electronic configuration of transition states. So now the answer with you, that which transition state is most stable? Which transition state is most stable? This TS1 is most stable. So in most of the cases,
Nucleophile.
yes, migrating group migrates in the form of nucleophile. Clear to everyone?
Yes, sir.
Okay. Now we can see the different types of migrations, right? Different types of migrations, like general form we can see. Plus and R, right? So this 1, 2. How many electrons are there in here? There are 6 electrons. This is electron deficient. So this group migrates through transition state, and we will get this type of carbocation. So this is the migration at electron deficient carbon, but this time this is positively charged. So migration at electron deficient carbon. And carbon, right? One more type of electron deficient carbon we may get in different reactions, like how many electrons are there in the valence shell of this carbon? 6 electrons. So this is a neutral species, something equivalent to what? Carbenes. So here also we can get the rearrangement. And here the R will migrate in which form? In the form of nucleophile. This will move with its electron pair to here, and we will get this type of product. And this pair of electron will move like this, right? So this is also migration at electron deficient carbon. Another type of rearrangement we can see where migration will take place at electron deficient nitrogen, right? Electron deficient nitrogen. How many electrons are there?
Seven.
Electrons. This is also electron deficient. So this R will migrate with pair of electrons, and this will move like this. So we will get this type of migration, right? So this is also migration at electron deficient nitrogen. Similarly, we may have this type of migration. Suppose that this, so this is also have 6 electrons. So this will migrate like this. So we will get like this, right? So these are the different kinds of what? Migrations, and all these migrations in all these migration, the migrating group migrates in the form of what? Nucleophile. In the form of nucleophile. Okay. So first we will take this, the different reactions involving the migration of migratory group in the form of nucleophile, right? So first I am taking here my rearrangement to electron deficient carbon. Rearrangement to electron deficient carbon. And first example I am taking here, Wagner-Meerwein rearrangement. Wagner-Meerwein rearrangement, right? So we should write some important feature of this rearrangement. So what is the most important feature of this rearrangement? That this rearrangement involves the rearrangement of less stable carbocation to more stable carbocation through the migration of alkyl, aryl, or hydrogen, which leads to the formation of more stable carbocation. So this involves the 1,2 migration of hydrogen, alkyl, phenyl, or alkyl or hydrogen to produce more stable carbocation. More stable carbocation. Right? Clear to everyone? What is the driving force for this rearrangement?
Yes, sir.
Driving force for this reaction? The stability of carbocation or the stability of rearranged carbocation. If we are getting tertiary carbocation from primary carbocation after rearrangement, so that is the driving force, because tertiary carbocation has less energy. So that the amount of energy by which the tertiary carbocation decreases, the stability increases by that factor. So driving force is basically the stability of carbocation, right? Formed after rearrangement. Right? So we can take a simplest example for this. Wagner-Meerwein rearrangement. Suppose that if we have system like this, suppose that we have a system like this, and we have taken this with the H plus. So see, in this molecule, we have only the nucleophilic center here, oxygen lone pair. So this will attack on H plus. So what we will get? And this will cleave one bond to eliminate water, minus H2O. Now, which type of carbocation is this? Secondary carbocation. Now, if we put this number 1 and this is number 2, So at number 2 carbon, we have methyl groups, 2 methyl groups, and 1 hydrogen. So as per the basic point of this rearrangement, which group will migrate? Methyl will migrate or hydrogen will migrate? You can answer in the
Hydrogen.
box only, right? Don't speak. Methyl will migrate or hydrogen will migrate? Hydrogen will migrate, because after migration of hydrogen we will get tertiary carbocation. But if methyl will migrate, so we will get again what? Secondary carbocation.
Secondary.
So hydrogen will migrate. So here hydrogen will migrate in the form of H plus or H minus. Hydrogen will migrate in the form of H plus or H minus.
Minus.
H minus. So 1 to H minus shift in the form of nucleophile. Here, if we take 1 to Me minus shift, right? But this carbocation is less stable, which we get after this. So the major this hydrogen will migrate through transition state and we will get carbocation here, right? Now, if we heat this, so hydrogen will eliminate from here. So we will get this type of product. So this is one of the example of Wagner-Meerwin rearrangement in which hydride shift is taking place to make the more stable carbocation. It is clear to everyone? Now we can see some different example. Suppose that if we have this type of system, right? And here Me and Me, and here OH. So suppose that if we have taken this with H plus, so what we will get? We will get Me and M, right? So here also alkyl group, here the migration of alkyl group is taking place, right? Now you can very easily, very simply understand this H plus will attack here and we will get protonated. And loss of water. And now 1 to methyl shift, right? This methyl will migrate with its electron pair. And positive charge will come here. So you will get this product. And all of you are knowing that from here and from here we cannot eliminate hydrogen, because at bridge head carbon, pi bond should not go here, because it makes the structure planar, and it is not a planar structure. This is a rigid structure by cyclo compound, right? So here why alkyl migration is taking place? Due to the formation of more stable carbocation. So this is the driving force here also, right? Clear to everyone this example? Okay. Now, one more similar example. H plus. So if you take H plus here, so what we will get? The product is what is the name of this compound? Anybody knowing? Isobornia. And this is camphene. So this also involves the Wagner-Meerwein type rearrangement. So see, whenever you consider this type of complex structure, you always prefer to put the number to the different carbon, and this will help you to understand which bond is cleaved and which bond is migrating, right? So I'm putting number here: 1, 2, 3, 4, 5, 6, and this carbon is safe, right? So 1, 2, 3, 4, 5, 6. This numbering could be according to the IPAC or without IPAC system. Don't worry, because we are just trying to find out the correct structure, right? So see, carbocation will generate here at carbon number 2. Carbocation will generate here, right? Something like this. Again, put the number here: 1, 2, 3, 4, 5, 6, 7. Now, which bond will cleave? Will this bond will cleave? This bond will cleave to migrate here, to put the positive charge here? The answer is no. This bond will not cleave, right? This bond will not cleave. Anyway, this bond, if cleaved, so this positive charge will come here, that is sp2 hybridized. Again, this will make a problem. So here, the group, this bond is, bond between 1 and 6 if cleaved, and this carbon number 6 makes the bond with the carbon number 2 and make this carbon number 1 free. So now this, once this carbon number 1 is free here by cleavage of 1,6 bond, so positive charge could come here, right? So we can make this cleave this 1,6 bond and make a bond with the carbon number 2, right? Carbon number 2. So in this way, you can visualize very easily what is happening. Now put the number again, same number, carbon number 1 is here, carbon number 2 is here, carbon number 3 is here, 4 is here, 5 is here, 6 is here. Now see, between 2 and 6, we have made a bond. Now this carbon number 1 is free and this is positive charge will come here, right? Okay, now we can rearrange this structure